This is an example of a free-fall projectile motion problem in 2 dimensions. A cannon fires a projectile at an angle of 57 degrees from the horizontal and an initial speed of 24 meters per second. Find the horizontal and vertical components of the initial velocity at the time that the ball is leaving the cannon. Okay, so first I'm going to draw the ground. And let's put the ball here that's going to be launched on the ground at the current time. I'm going to draw its initial velocity vector, which I'll call VI. As the projectile travels through the air, we expect to see this kind of motion map. A parabolic path for the projectile, where it leaves the cannon, reaches a peak, and then comes back down to level ground once again. Now, one of the first things we want to do in analyzing two-dimensional motion of projectiles is to find those horizontal and vertical components of the initial velocity. So we like to imagine that there's an x and y axis here. Project our vector head down to the x-axis. And then this will allow us to create the horizontal component, which I'll draw as an arrow. But oftentimes I'm going to draw components as dashed arrows, just to differentiate them from the original velocity vector. Don't want to get them confused. Let's label it VIX. Now we'll trace the arrowhead over to the vertical and create for ourselves a vertical arrow, which will be called VIY. Now, in past videos, I showed how to find components of a vector. They have the formulas VIX equals VI times the cosine of the theta in standard position. And we also have VIY equals VI sine of the theta in standard position. Now the angle is 57 degrees. My scale is a little off. I suppose the vector arrow should be a little higher. Let's plug in the initial speed of the cannonball, 24 meters per second. Cosine 57 degrees. 13.1 meters per second. That's VIX. And keep in mind that VI has a magnitude of 24 meters per second. Now let's find the vertical component. It's 20.1 meters per second. All right, now that we have those two things, we can find the time that the cannonball takes to hit the ground and the range, which is how far the cannonball travels horizontally before impact. Now we have to decide which of the motion formulas should we use at this time. We could focus on the horizontal dimension, And if we do, then we want to use constant velocity formulas. Or we could decide to focus on the vertical dimension. And in that case, we would want formulas involving acceleration. Now, sometimes it can be tough to tell which formula we should start with. So you may wish to write down what you have and what you want. So what are some quantities we have? We know everything about the initial velocity. Now, we don't really care too much anymore about the total initial velocity. When we're doing two-dimensional motion problems, we want to break it up into x and y components on purpose because we have to work with them independently. So notice that we have Vix, 13.1. We have VIY. Is there anything else out of all the different motion quantities that we have? Well, there's one thing in free fall that you can always count on. We always know the acceleration due to gravity in free fall. It's something that's constant no matter what the object is that Earth is pulling on, as long as air resistance is negligible. Whenever that's the case, we know that the acceleration in free fall is going to be 9.8 meters per second squared in the negative j direction. So we have that as well. Are there any other things that we could add to our list here? Notice that this formula involves the position y. So if we were going to assign a position to the ground, what should we assign? What should we call it? I'm going to call the ground y equals 0. That's actually totally arbitrary, it's my choice, but often that is an easy choice that we can make for the purposes of problem solving. Alright, so those are all the things we have. One of the things we don't have, though, is the time. And that's what we're being asked to find in part B. Okay, is there anything else that we have here? Let's look at the symmetry of the parabola. And let's also draw the path that the cannonball takes. I draw the path in order to show the symmetry of it. And we know that the velocity is always tangent to the path. We also know that the horizontal velocity component does not change with time. But the y component of velocity does change. Look how it got shorter than it was before. Now when we get to the peak, something unusual happens. We know that the horizontal velocity vector can't change. That still has to be there. But when we're at the peak, we're in a place where we're neither moving up nor down. So we won't actually have a vertical component of velocity at that time. And that's really critical for these problems. That means that the Vy suddenly becomes 0 at the peak. Notice that we have a Vy of 20.1 at this time. We would have a Vy of perhaps about 10 at this point. But when we get to the peak, the Vy becomes 0. After the peak, our projectile will be traveling downwards. And then finally, when we get toward the ground, another interesting thing happens. The final velocity vector is going to be symmetrical to the initial velocity vector. They're actually going to have the same size arrow, but whereas it was going up at 57 degrees when it was launched, the ball will now be coming down at 57 degrees from the horizontal when it lands. Not only that, but the VFY component here is going to be equal and opposite to the VIY component that we had when it was launched. That's an important fact that we can use to solve these types of motion problems. And of course, the horizontal component remains 13.1 meters per second throughout. With all that in mind, we can say that we know what VFY is going to be. It will be negative 20.1 meters per second. I bring that up because we'll see VFY in some of the formulas. Okay, now let's try to identify a formula where we could plug in everything except the time. Take a look at all the options and decide which one is best here. Okay, this one jumps out at me. The formula is VFY equals AYT plus VIY. We have VFY, we have AY, and we have VIY. So we can solve for the unknown time t. Let's plug everything in. We always want to keep track of the directions in these types of problems. So the VFY, because it's down, will be considered negative. AY will be the acceleration due to gravity, which is listed right here. And then the VIY is going to be positive 20.1 meters per second. Let's solve for t. I get 4.10 seconds. This is the answer to B. So that's how long it takes for our projectile to come back down to ground level. The cannonball hits ground 4.10 seconds after the launch. Now we want to find the range. How far horizontally will the cannonball travel before landing? We're talking about this distance here. And of course it has the letters delta x. So whereas in order to find the time we analyzed the vertical dimension, In order to figure out how far the projectile goes horizontally, let's analyze the horizontal dimension. So we'll use this formula right here. Delta x equals Vx times t. Now the velocity in the horizontal dimension is going to remain constant. It will be 13.1 meters per second. We want to multiply that times the 4.1 seconds that we had found previously. The delta x is 53.7 meters. And that will be the range of the cannonball.